This is the third lesson for unit number 6 for our AP Calculus. And just to give you kind of a feeling for where we're at with this chapter, the first couple of days of this chapter, we're looking at methods to actually accomplish some antiderivatives. We looked at two of them specifically. We looked at this one, substitution, where you have this blob and then the derivative of the blob hanging around. And then on the second day, just out of interest, we looked at this method called integration by parts. And those are kind of the tools that we're going to use, but they're not the problems that we're going to do, right? They're just some tools that we're going to use to solve the problems we're going to do. Now, one reason why you might want to know how to do an antiderivative, whether it's by substitution or whether it's by parts, is to find the area under a curve. But there's also another time when you have to actually do antiderivatives, and that's when you're solving some things called differential equations. And we're going to start off by looking at first-order differential equations, and then we're going to bump our way up to actually some what are called second-order differential equations. So a first-order differential equation is just an equation that's written in terms of the first derivative. You're going to see the first derivative of the answer sitting in the question. Usually the solution is a whole nother equation, and many real-life questions are based on these differential equations, these stories written in terms of derivatives. Now sometimes you get really lucky, and you can do a nice simple little method here. It doesn't work all the time, but first-order differential equations written with only independent variables on the right-hand side. Okay, you'll see what that means specifically here in a minute, but if that's the case, if it just has the independent variable over on the right-hand side, they're actually not very challenging. It turns out you can come to the answer just by integrating once. Now, to do that integration, you might have to go and do integration by substitution or maybe integration by parts, but you'll only have to do it once and then you're totally done. Now, I'm going to use physics stories as a way to kind of bring in this idea of differential equations. So just a little physics reminder of the various bits of vocab we've got out there. S is going to talk about the position of an object, its location, and V is going to be the velocity, and it's actually just S prime. A, the acceleration, is actually S double prime of t. And some things you can do, if you take the absolute value of velocity, then you're going to be looking at the speed of the item. Now, two choices for integrating. If you integrate just straight up velocity, including any negatives, then you'll actually find the displacement for the object. But if you integrate the speed, then you end up finding the distance that it travels. So depending on whether you want displacement or distance, decide whether you want to put absolute value bars on that integrand or not. Okay, well here we go. We're going to dive right into this idea of differential equations. We're going to solve something that sometimes people call initial value problems or boundary problems, kind of interchangeable for those names. Little physics story. It says the acceleration of an object in free fall is negative 9.8 meters per second squared. And it says please go and find the velocity as a function of time. Find that function if the item does have an initial velocity of 20 meters per second when time is 0. So I'm just going to show you an option for how to attack these questions. Now, you might be able to do this just with some physics 11 or physics 12 knowledge, but here's kind of a different way of looking at it. So by into doing it this way, even though you could do this maybe with physics 11 and physics 12, the idea is, doing this on an item, a thing that you know, so that you have some comfort with the topic, but now you do want to practice this calculus method. So the acceleration is negative 9.8. That's how you might write it in physics. Let's talk about how you might write it in terms of calculus. You might say, hey, look at this. This first derivative of v, this is why it's called a first order differential equation, is actually equal to negative 9.8. So what I've got, I don't have any v's over on this right-hand side. I might have t's, and here I don't even have t's on the right-hand side. So the good news is no v's. Okay, because that's going to be something that will actually happen in the next few lessons. But on this side, there are no v variables on this side. So here we go. I can actually find the velocity by doing nothing but integrating this acceleration that we've got, integrating this negative 9.8 dt. And it's done pretty quick. I can find out that the velocity, which is a function of time, is going to be negative 9.8 t but there's a constant in there, some sort of arbitrary constant. And that's where it gets this name boundary value or initial value. I've got some information that I can actually put into this story. I know, according to this story here, that the velocity, when you put 0 in for t, needs to work out to be 20. Well, just looking at this thing that I made, I have this negative 9.8 t plus c. So looking at that last line down there on the left, I could say, okay, negative 9.8 times this information that you're giving me. You're saying, well, at times 0, 0 for t, and then I add on my c, I need to get 20. That's required. All right, well, this is going to unfold pretty quick. It looks like 0 plus c is equal to 20. Okay, so the c, this missing constant, needs to be at 20. Here's my final answer. The velocity at any time for this object is actually negative 9.8 t plus 20. Not only will that work at time equals 0, but that'll actually work at any time. So you've just solved a first order differential equation. It was an equation back here. I'll show you where I started. Way back over here, that was written in terms of the derivative of v. And people are like, well, go get v, right? Well, you gave me the derivative, so I have to do an antiderivative. All right, let's try this out again. And I'll show you again what I mean by this issue of no v's, no dependent variables on that right-hand side. So example 2, the velocity of an object might be given by this story, 4t minus 5, with some boundary value, some initial value, that the position at time 8 needs to be 100. And then they're asking, can you go and find s at any time? Oh, and then can you also go and find the distance it travels for 5 seconds? Sure. But let's start off with the first task of just generally finding this position. So they're telling me that velocity, which is actually the derivative of s, first derivative of s, is equal to 4t minus 5. Okay, now here's what makes this question so nice. We're going to look at ones like this today. So this lower variable here, this is the independent variable. And it looks like it's t. And as I look over on the right-hand side, I see only t's. I don't see any s's over on this right-hand side. Nothing but this 4t minus 5. That tells me that this question is actually not all that challenging. And I can find the answer for s, s at any time t. I can get there by just simply integrating this 4t minus 5 dt. That's all I'll have to do. Okay, well, this is going to happen pretty quick. It looks like s at any time t, if I do an antiderivative here, so this one's just in powers, I can do that pretty quick. Looks like we'll have a 2t squared minus a 5t. Oh, but also a constant. There's a plus c in there. And at first glance, I'm not too sure what that c would be. But then they gave me some information. They said, oh, well, hey, we want to tell you this, that the position at time 8 has to be 100. So I'm going to use that info right now, that boundary value, right? I'm going to make sure that this story that I've got actually agrees with that idea, that the position should be 100 when I put 8 in for t. So then I would have this. I would have s when I put that time in of 8, right? That would be equal to 2 times, again, I'm putting that time in of 8, and that gets squared, minus 5 multiplied by that time of 8. When I do that, this c is just right. It's the perfect size c, so that when I add that c on, I end up with their story of a position of 100. Okay, well, this unfolds reasonably quick here. I've got 8 squared, so 64, and then doubled up, 128 minus 40. Looks like we've actually got, just in terms of constants here, got an 88, and then plus this c has to be 100. Looks like this story has to have a c value that's 12. There's no way around it. It's going to have to be 12. And so I've now accomplished this task. I've done the first part of this story. They've said, oh, go and find s as a function of time. And I'm going to take my original one, but I'm going to now put in this very specific constant. So I'll have 2t squared minus 5t. And this story, this one, needs a plus 12 in order for this to work. So that should do it. That should be the solution to this differential equation. So the solution to this differential equation, it's kind of neat. It's a whole new equation, right? This one tells you exactly what the position is at any time. Well, they had a follow-up though. They said, "Oh, hey, would you mind going and figuring out the distance that it goes for the first 5 seconds? Could we go and do that?" Sure, yeah, we can go and do that. I've actually got a couple of plans here. If I integrate just simply velocity dt, then that would be displacement. Not exactly what they're asking for. But if I integrate the absolute value of the velocity dt, then I'm going to end up getting distance. So that's what I'm going to need to do. I'm going to have to take that solution there, that velocity that they gave me, 4t minus 5, and I'm going to have to integrate its absolute value. So I'm going to go from their request here, time 0, out to time 5, and I'm going to do the absolute value of 4t minus 5. Once I put those absolute value bars on, now I'm talking about speed. Okay, choices. How do you go about doing this? You can do it by hand if you want. You'd have to notice that when time is 1.25, this 4t minus 5 is going to change sign. So you'd have to integrate first to 1.25 and find out how much distance you've got, and then integrate again. That can be done, or you could just ask your calculator, right? If it doesn't say not to, then you could just say, "Oh, okay, hey calculator, can you help me out here?" And let it do all the work, right? So I'm just going to go math, option number 9. What do you want to integrate? Well, I need to do the absolute value of that velocity, so just ask for it, right? Just go in there and say, yeah, I need absolute value of 4 times that independent variable minus 5. I'm using x's for t. There's my function. I'm using x's, and I'm going from 0 to 5. Let it do the work, right? It'll deal with the fact that for some of the time that 4t minus 5 was actually negative. Okay, and so the answer there ends up being 31.25. Now, if you can't use your calculator and you have to do this by hand, well, that's trickier. It could be done. Here, I'll just do it in a different color here. You'd have to say, geez, does this velocity, does it ever actually hit 0 along the way? And you'd solve this story. You'd be like, oh, okay, does this ever happen? Oh, yeah, it does at time 1.25. So you'd actually have to, if you don't have a calculator, you'd have to integrate from 0 to 1.25, and you'd integrate that 4t minus 5. You can do that by hand, right? That's doable, right? You can accomplish that. And then you would integrate from 1.25 to 5. And if I'm not mistaken, when you go about doing that, what you're going to find is this first one, I believe, is negative 3.125, I'm pretty sure. And then the second one, I'll double check this, but I think that's 28.125. So that could be done, without a graphing calculator. I'm going to cheat a little bit just to make sure I'm not giving you wrong answers here. I'm going to take off this absolute value business. So I don't need that. Okay, so I'll delete this. If I only integrate it just like that, from 0 to 5, I would actually get the sum of these two things. Those would cancel out a little bit. And it says, oh, the displacement's 25. Okay, well, I don't want that. But what I could do is say, well, let's integrate from 0 to 1.25. And then the math says, oh, well, you're going to back up 3.125 units. And then I could integrate from 1.25 all the way to 5. And then that's when I see, oh, yeah, we're going to go forward 28. So if you want to talk about, actually we can see them right here. If you wanted to talk about displacement, you would just add those up and say, oh, that's 25. So that's displacement. But if you want distance, you would go 3.125 plus the 28.125. And that ends up being this 31.25. So that is the distance that you're going to go. So you got to decide, right? Do you want to be finding displacement or do you want to find distance? And they had asked for the distance in that story there. Okay, before we go and take a look at what are called second order differential equations, let's just throw our skills now at a little story here. What do we got? Find y, so find some function of x, right? It's y of x. If the derivative is 2x minus 5, and the actual curve, which is going to be complicated, it's going to be a parabola, is tangent to 3x minus 19. So if I was doing this, I would start off with this differential equation, right? Where they're saying, hey, dy dx is equal to 2x minus 5. Now, I'm pretty lucky right away because at the beginning, there's nothing but independent variables here. So there are no y's over on this side. That's going to change in the next lesson. But for now, take it. All you have to do is an antiderivative. You just have to integrate. So y, which is going to be made up of x's, would be x squared minus 5x, but plus a c. And we need to do a fair bit of work right now just to figure out what that c is, right? I have no idea at first glance what number's actually going to go there. Here's what I do know. Apparently my answer is looking like a parabola of some kind. And it's going to be sitting on the page nicely with this tangent line 3x minus 19. Now I'm not going to draw this perfectly to scale, but I'll be roughly close here. I'd have to have a slope of minus 19, so it's way down here. Sorry, a y-intercept of minus 19, which is way down here, and then a slope of positive 3. So I don't know, maybe something kind of like that. And then this parabola comes in, and it's going to have one point where it touches it. It looks like it's a right side up parabola, and I really don't know where it touches it at all. I don't know the x or the y value. Now, I'm going to cheat because I haven't looked ahead, but it does kind of come in and go and makes tangency right there. So it's like this, but we don't know this point at all. I don't know its value, right? It's like, hey, what is that point, right? And I just don't know right off the start. But there is one thing that I do know, just from my knowledge from grade 10. This line here, this thing has a slope that's equal to 3, right? So this tangent line, it's got a slope that's equal to 3. So at the moment of tangency, right at that big blue dot that I've got there, that blue parabola must have a slope of 3. I'll leave that in as a little note. Okay, so our answer so far looks like this, and it looks like it must have a slope equal to 3 at that point. Okay, well, let's just go and find out, when that happens, right? Here's what we know. The derivative for that, y prime, they gave it to us, right? They said, oh yeah, the derivative is 2x minus 5. That's going to have to equal that 3 that we've got there, right? It's got to be that same slope as that red tangent line that I've drawn in. So we can actually figure out at least the x value pretty quick. It looks like 2x is equal to 8. It looks like x is equal to 4. Hey, we're getting close. We're getting close. Looks like the x, this thing right there, that's got to be 4. I don't know what the y value is yet, so I'm going to go after that and see if I can find it. I'm going to check out that red line, right, and see what its y value is. So that's my next task. So next step, hey, what's the y value? Not too sure. Well, I do know that that point of tangency is also on this line, 3x minus 19. Let's go and take 4. Let's drop it into there. Okay, 12 minus 19, that's a negative 7. Okay, so we're really close here now. Right? This point of tangency is -7. So the actual point where we're touching, where the two graphs touch each other, is 4, -7. That point, it's not only on the red tangent line that I've drawn, but it's also on the parabola. I'm going to use that as my boundary value. And by boundary value, I just mean the little clue, the little bit of information that I can use to find out what the C is. So going back to my work, I was so close very early on. I'm like, oh yeah, I think the answer, this y, which is a function of x, it's x squared minus 5x. But there was this plus c, right? I'm like, oh, what's that c? Well, I do know that that boundary value has to be on this graph. I know that when you put 4 in for x, you have to get -7 for y, right? So that narrows things down quite a bit. So I'm going to have this 4 going in here, getting squared minus 5 times that number, which is 4. That's got to work out to be -7. So what do we have here? 16 minus 20. Okay, it's looking like -7 is equal to -4 plus c. Oh, okay, so c is equal to -3. We're finally done. Here's my answer. My solution to their equation is a whole nother equation. Y is equal to x squared minus 5x minus 3. That one's done. So it took a little work to get that -3, but we managed to get it there. Now, looking back at this kind of big picture, back up at the top, when we had this differential equation, almost the first thing I wrote here, I was pointing out, hey, there are no dependent variables, no y's, right? That's what makes this a nice story where you can just simply do an antiderivative and you're there. We're going to do that still on these next few, but these ones are now going to be what are called second order differential equations, but there'll be some easy ones. So a second order differential equation is one that is written in terms of the second derivative. And the solution is a whole nother equation. So you're given this equation, you're told to solve it, and you're going to come up with another equation. And if you're lucky, and you've only got independent variables on the right-hand side, right? This doesn't happen all the time, and it won't happen in the next lesson. But if you're lucky enough to have that, you can solve it just by integrating twice. Okay, just like last time, I'm going to throw a physics one at this. Don't solve this with physics, though. The only reason why we're doing a physics one is so you have some comfort level with the story, but you want to do this one with some calculus. So it says an egg is thrown straight up at 39.2 meters per second from the top of a really tall building. It's 44.1 meters above the ground. And we want to know when does this thing hit the ground. So okay, here's my building, and we're going to be up at the top of it, and somebody's throwing some eggs. Doesn't sound safe, but they're doing it. So here's this egg, and it's going to go up into the air, and I guess stop rising, and then go down to the ground, and then splat down on the ground down below. And that building is 44.1 meters tall. And right at the start, people are throwing this thing up with an initial velocity of 39.2. All right, so I want to do this as a differential equation. I just want to use physics as a way to show you that this differential equation thing is kind of neat. So we know from physics that the acceleration is negative 9.8. Yeah, the units would be meters per second squared. Great. But let's now convert this over to some sort of calculus story. Let's go and say, hey, A is the second derivative of S. So S double prime, or if you wish, you could say d squared S dt squared, right? That's how Leibniz would write it, is equal to negative 9.8. Now, good news, this right-hand side doesn't contain any s's, okay? So it doesn't even have t's either, But, I'm really actually pretty happy that there are no S's over on that right-hand side. That's going to make things pretty nice. All I have to do is actually integrate this story twice, and we should be able to figure out what's going on. We'll spread our work out here over a couple of pages. So, off the start. First antiderivative. That should get me to S prime, otherwise known as velocity. I will get there if I integrate this negative 9.8 dt. Okay, so t's are the variable. Good thing to tell me that because I wouldn't know. There's just this number, negative 9.8. But once you tell me that t's are the variable, I can do this. So the velocity is actually negative 9.8 t plus some constant. Now I'm going to call this constant number 1 because we're going to get multiple constants in this story. Each time we do an integration, an antiderivative, we're going to get a constant. Okay, so let's go for our first initial condition and see if we can go and find this C1. I need to know some boundary value, some bit of information about velocity. And I do have one. I'm told in the story, right, they initially said that the velocity at time 0 is going to be 39.2. Well, if I use my machine that I've just made, that would be negative 9.8 times a 0 plus C1. And their story, they said that this was going to be 39.2. So I'm just stealing their information, it's right here, and saying, oh, okay, that calculation must result in an answer that's 39.2. Okay, fine. 9.8 times 0 is 0. Add the C1, get 39. Okay, C1 has to be 39.2. So we can refine our story here and say that S prime, which is the same thing as velocity, right? It's a function of t. We can say, hey, that's got to be negative 9.8 t plus 39.2. I don't have to say C1. I can narrow this right down and say, oh yeah, no, in this story, it's a 39.2. Okay, well, let's keep going with this. Let's keep going with this. We've got one antiderivative done, but we haven't quite got to the point where we have position. So I need to do this again in order to get to the point where I can tell people what S looks like. They gave me S prime. Sorry, they gave me S double prime, and with a little bit of integrating, I got to S prime. I've got to do it again in order to get to just straight up S. So yeah, I just need some more space here. I'm super happy that on this right-hand side, that all I see are T's, and I don't see any S's in there, right? So this is good. Okay, so just only T's. That's okay. That means we can just do an antiderivative. If you want to talk about S, we have to do an integral, an antiderivative of negative 9.8t plus 39.2. And t's are the variable. So yeah, okay, this is going to go pretty nicely. Looks like we're going to have a t squared with a 1/2. So we'll have s of t. We're going to have a 1/2. We're also going to have this negative 9.8 floating around. We're going to have a t squared, and then we're going to have a 39.2t, and then another constant. There's this C2. And I want to know what that C2 is. So just like last time, I'm going to go and do a little substitution in there. I'm going to put in the time that they mentioned. They said at time 0, we're going to have a position of 44.1. So let's go and substitute in. I'm running out of room on this page, but I'm going to go at this point and substitute in time 0. So I would have 1/2, negative 9.8, 0 squared, plus 39.2 times 0, plus C2 has to be their call. They said it 44.1. Okay, well it looks like C2 has to be 44.1. That's the only way that that's going to work. We can go over to the next page. There's room to finish this question off. But it looks like we're now ready to tell people what we've got. So the position at any time that people want to know, it's going to be 1/2 negative 9.8. And yes, you could write that as negative 4.9, but I wanted to write it that way because it kind of feels more like physics 11 or physics 12, right? 1/2 AT squared, and then plus 39.2t. Now, if this was physics 11 or physics 12, we would just say, oh yeah, we're done. 1/2 AT squared plus that VIT, but that would be displacement. That would be D. If you actually want to know the true position, you have to put in a 44.1. So now we won't be talking about the movement, but we'll be talking about where it's actually located. We still haven't done their question, but it's close, right? They had a little request here. They said, hey, when does it hit the ground, right? They want to know what time it hits the ground. So we've got just enough room to finish this off. So you want to know when it hits the ground? Well, last time I checked, the ground was down there at location 0. So we can solve this pretty quick. And so their next request is when does it hit the ground? Well, you want to know that? Let's go and put in 0 for the location. So we've got 0 is equal to negative 4.9 t squared plus 39.2t plus 44.1. Okay, well, it's quadratic, so you can fire up your quadratic program. You could factor out a negative 4.9 too. That actually works reasonably well, but you could use your quadratic program on your calculator if you want. But if I factor out a negative 4.9, I get the feeling this is going to extract out of there pretty nicely. Let's check. So 39.2, does that divide by 9.8? Yep, a 4. And 44.1 divided by 9.8. Close, a 4.5. Okay, that's not super nice. So maybe we'll just go for the, let's just go for the quadratic program, see what that says. Okay, so if I try this with the quadratic formula, let's try that out. So I'm just going to put those numbers in. For A, I've got negative 4.9. For B, got 39.2. And then for C, 44.1. And I get two answers, negative 1 and 9. The negative 1 doesn't make any sense. That would be in the past. So it makes sense mathematically, but it doesn't make sense with our physics story. So yeah, I would say, all right, it's going to take 9 seconds. That egg was going super fast up in the air. It's going to take some time for it to come back down and then hit the ground. And it'll be at time 9. And then their last question is, well, how fast is it moving when it hits the ground? Well, we already know that it hits the ground at time 9 seconds, right? So those two things are the same. And halfway through our solution, we had actually found s prime of t, the v of t, right, the velocity. We already saw that go by. That was negative 9.8 t plus 39.2. So that works for any time. Let's go and try it out for one very, very specific time. Let's go and try it out for 9 seconds. So the velocity at time 9 seconds, all I have to do is just substitute this in. And when I tried that out, I ended up getting negative 49 meters per second. So the negative just tells you that it's coming down to the ground, which makes sense, right? By the time it's come all the way down from that building, from its maximum height above the building, it's going to be heading with a negative velocity down towards the ground. Okay, so we're doing pretty good. Now we're going to do one last big question. really big question. It's going to take a couple of pages. And it's just another physics story. We're going to look at what happens when they do what's called rocket staging, where one stage of a rocket fires for a while. In our story, it's going to be for 5 seconds. Okay, that's going to be this section of the story here. And the rocket accelerates, it picks up speed. Then it takes them a little bit of time, hopefully not too long. The rocket will be coasting while they shut the first stage off. So we're going to go and coast for 2 seconds while we fire up the second stage. And then we're going to run the third stage engines for a little bit longer. Now, just to keep the numbers reasonable, we're just going to run this whole story only for 12 seconds to try to figure out where this thing would be. All right, so we're going to break this up into a whole bunch of stories. For the first 5 seconds, okay, just for those 5 seconds when the first stage is running, so I'm talking about the time on the clock that would go from 0 out to 5. During that time, they're telling me that the acceleration, that's s double prime, right? Same thing. They're saying s double prime is equal to 8 plus 6t. So this acceleration improves as time goes by. That's what the plus 6t is going to do. And that's because the stage gets lighter, right? There's going to be less fuel on board. Now I'm going to split this little box up so that I can do one calculation on the left and then another one on the right. Now I'm super happy that there are no s's on the right hand side, only t's. So we can actually solve this differential equation, this equation written in terms of derivatives, just by integrating. So my s prime, right here I go, I'm going to solve this equation. It'll be 8t plus, now it's going to be a t squared, and then there'll be a half meeting up with a 6, that's going to be a 3, plus a constant. The first of many in this story, so let's call it C1. Now, they said in the question that it starts from rest and it starts on the ground, right? That was mentioned way back up here. So those are some nice initial values that we can use. Okay, so if you start from rest, then s prime is equal to 0, and you start on the ground, so s is equal to 0. Well, since this thing starts from rest, we could say, hey, the s prime at time 0, that would be 8 times 0 plus 3 times 0 squared plus c1 has to be nothing so that we can actually start from rest. And that solves c1 pretty quickly. c1's got to be nothing. So we can actually make this official. The velocity for the first 5 seconds, this only works for the first 5 seconds, would be 8t plus 3t squared. Let's take that up over here. Here's another differential equation to solve. 8t plus 3t squared. It's only got t's on the right-hand side. It's beautiful for just doing an antiderivative. So it looks like position would be 4t squared. Just doing some antiderivatives here. Plus a, well, this is just going to be a t cubed because you'd have a 1/3 bodyguard and then the 3, they're going to go away. And another constant, constant number 2. But again, we have some initial values. We're told that the position at time 0, which would be 4 times 0 squared, plus 0 cubed, plus c2, we're told that it starts on the ground. So let's put a 0 in there because it starts on the ground. And that lets us go and solve for c2. And it looks like this c2 is equal to 0. Okay, and you might be thinking, oh yeah, they're always going to be 0, or maybe, oh yeah, they're always going to be the initial values. Well, be careful. Take a look at what happens in the next few little segments here. But it is true here that c is 0, and I could say that for the first 5 seconds, the position is given by this machine, 4t squared plus t cubed, just that. Now, let's look at the handoff. That's what I'm going to call it. What about that moment right at the end of the first stage firing? Let's go right to this limit at t is equal to 5. Okay, right to the end of this story for the acceleration being 8 plus 6t. I'm going to go and find out, just as a limit, what is the velocity at time 5. So using this, this relationship right here, I'm going to say, okay, well, right at 5, I mean, technically this doesn't work at 5, it works just up to it, but I'm thinking about it as a limit. So this is okay. When I do that, I find that the velocity, when the first stage is finished firing, it's pretty impressive. It's 115 meters per second. Okay, well, what about its location? Let's go and do a limit for this machine as t limits out to 5. So the position at time 5 would be 4 times 5 squared plus 5 cubed. And when I tried that out, I found that this position, it was approaching this 225 meter point. Right? Kind of as a limit, because technically that first stage doesn't quite take you all the way up to 5, right? It would be just before it, but close enough for what we're going to do. So that's just the first section. Now, we have 2 seconds of free fall. So the physics people would say, oh yeah, it's going to accelerate down at 9.8 meters per second squared. It's still going to go up, right? But it'll be slowing down. So it's moving up, but accelerating down. Let's go and see if we can keep the clock running, right? I want to keep that time now starting at 5, and I want to go from 5 out to 7. And I'm going to do the same thing as last time. I'm going to scrunch it in a little bit now that we're experts at doing this and say, all right, we're told this differential equation is true. The second derivative of s is negative 9.8. So thankful there are no s's on that right-hand side. So I just do an antiderivative. S prime, otherwise known as the velocity, would be negative 9.8 t plus constant 3. Okay, I'm going to go and find out what that constant is. And you might think, oh, it's just going to be 115. Nah, it doesn't work that way. Not if you want to keep the clock running. You'd have to say, I want to put 5 in for t. I want to have 1 clock all day long. And I'll have that C3 be just the right value so that that answer hits 115. And I'll give you the number here. You can trust me. This C3 needs to be 164. Which means if you want to keep the clock running, measuring time from when you first launch your rocket, in this window of time, in these 2 seconds, it's actually this machine right here that's going to tell you how fast you're going. Negative 9.8 t plus 164. I'm now going to take that and go up over here and say, okay, s prime is equal to negative 9.8 t plus 164. I'm so thankful there are no s's over there on that right-hand side. So I can just do an antiderivative, and I can find out a position machine that works for these 2 seconds. And I end up with negative 4.9 t squared. You pick up a half, right, from that t squared, plus 164 t, and another constant, c4. Okay, well, I've got a boundary value. That transition, that handoff from the first stage, I know that this s, when you put 5 in at the beginning of this window, right, like right here, when you put that in, I'd have negative 4.9 times 5 squared plus 164 times a 5 plus this mysterious C4. I know that has to work out to be the end of the last window there. It'd have to be 225. And when you solve this, you get kind of a weird looking C4. It's not 225. It's negative 472.5. So for this 2 second window, where time starts at 5 and can creep up towards 7, the position machine is actually this, negative 4.9 t squared plus 164 t minus 472.5. That will predict correct position values, but only for those 2 seconds that occur between time 5 and time 7. Let's look at the handoff. What happens right at time 7 when this math no longer keeps working, right? It's good up until 7. So let's check it out right at 7 as a limit. I'm going to put negative 9.8 and then the 7 in here, plus the 164. And what I find when I go and check out that velocity, now remember, it's been coasting. The rocket's been off. We've been trying to fire up the second stage. This is the coasting time, right? These the time from 5 to 7 seconds. And so it's no real surprise to me that the velocity at 7 seconds, it's slowed down just a little bit. It's down from 115 down to 95.4 meters per second. The position at time 7, well, let's just go and substitute in 7. And what I find is this rocket, it's been slowing down but still going up. It still has a positive velocity, and it's moved up from the 225 meter mark, and it's now at 435.4 meters above the ground. And that gets you to time 7. But now at time 7, we begin the last 5 seconds where we're going to run another rocket stage. So this is going to go from 7 out to 12. Same plan. So what's the important stuff here? Well, I've got a second order differential equation. S double prime is equal to, in this story, 10 plus 12t. So if I want to know what S is, I have to integrate twice. I'm so thankful that there are only t's on the right-hand side. Integrating's not that hard. So I just integrate with respect to time, and I get a 10t. And this would be plus a 6t squared plus a fifth constant of the day. But I can go and figure out what that constant's going to be. I can say, hey, you know what? If I check out at time 7, right when this starts, if I go 10 times 7 plus 6 times 7 squared plus C5, I need to get 95.4. And when you do that, you end up finding that C5, it's just this weird random number, negative 268.6. So here's a machine that will work during these 5 seconds. The velocity at any time inside those 5 seconds is 10t plus 6 t squared minus 268.6. I can actually use that, might as well do it right now. I can use that to figure out how fast this rocket's going at 12 seconds at the end of the story. I would now substitute 12 in for t, and when I do that, I get 715.4 meters per second. That's how fast we're going. Let's go one more antiderivative though. We've got this first order differential equation right here. Let's go and see if we can integrate it. Right? So S prime is 10t plus 6t squared minus 268.6. So then S would be one more antiderivative, 5t squared plus 2t cubed minus 268.6t plus C6, some last constant here. Okay. When I end up trying this out at time 7, just picking it up from the handoff, if I say, hey, putting 7 in, I need to make sure that you're equal to the 435.4 that we saw. I'm going to just skip to the chase here. When I do that, I find out that constant number 6 ends up being 1,384.6, using the same techniques we've done 5 times now. I just don't have a lot of room left, so I'm just going to go for the answer here. So the position of the rocket during any one of these 5 seconds from time 7 to time 12 is 5t squared plus 2 t cubed minus 268.6 t plus 1384.6. Wow, that just fits. And then I can go and try it out and say, all right, well, at the end of the story, at time 12, when this rocket has finished firing, where are we? And we end up with 2,337.4 meters. So sometimes we've got to just link one story to the next, and that's where it actually gets the name boundary value, right? We've got these boundaries from one part of the story to the next. Key thing, right? Just kind of looking at this big picture, it was super nice that when we were doing these differential equations that we only had the independent variable, just t's over on the right-hand side, no s's. And that's going to change when we start the next lesson. If it's a second order one, well, you'll have to do a couple of those antiderivative moves.